Hello and welcome to the Daily Space. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Today, we are happy to be bringing you two special guests, Sophia Gad-Nasr and Cathrin Machin. The two have recently teamed up to bring some amazing science-based beauty into the world. And we're going to talk about their collaboration and the problems it is creatively solving in the second half of our show. It's Friday. And at the end of a long week, sometimes it's good to look back over the news cycle and find something adorbs to carry you into the weekend. Well, there is one extremely cute story, in my opinion at least, that we didn't have time to cover on Wednesday. That story? Well, it was the launch of tiny, cute baby squid to the International Space Station. 128 baby bobtail squid were launched on SpaceX's most recent resupply mission. These tiny sea creatures are just 3 millimeters long, but have complex bodies that, like human bodies, interact with a microbiome of helpful bacteria. While we do our best to study how astronauts are affected by microgravity and their microbiome is affected by microgravity, we can't right now launch 128 astronauts all at once to do a nice controlled experiment. This is where squid come in. They were launched in a semi-frozen state to save them from a lot of the stress of takeoff, and will now be thawed, allowed to do their happy baby squid thing, and ultimately returned to Earth for study. Why squid? Well, it turns out that as different as humans and squid may seem, our immune systems are actually pretty similar to that of our cephalopod cousins. In an interview with the BBC, researcher Jamie Foster explained, as astronauts explore space, they're taking with them a company of different microbial species. And it's really important to understand how these microbes, collectively called the microbiome, change in the space environment and how those relationships are established. As a reminder, the microbiome living on and in your body does everything from aid in digestion to eating up the moisture around your eyes while you sleep. While it's gross to think about, it's actually super cool and super necessary for our health. So, while we do need a dose of cute, I do have to admit that not everyone is going to find squid, not even baby squid, all that cute. So for those of you who need a different piece of adorable news, I bring you an adorable rover. You can get a high-resolution version of this image on our website, dailyspace.org. And this image shows the cuteness that is the Chinese rover. Yesterday, China released the first photos taken by its Zhurong Mars rover from the surface of Mars. This group photo was taken from a small camera dropped by the rover 10 meters from the landing site. The robot equivalent of setting your phone down on a bench to take a picture with a friend. This image shows the rover and in the background, the landing platform. The rover was delivered on top of the lander and rolled off on a ramp that you can just make out on the edge of the image. The rover itself looks remarkably insect-like, with 2 camera eyes and large curved solar panels that remind me of butterfly wings. The gold of the rover's body stands out to the red rocks of the Martian surface. It's just pretty and makes science. We need more of this. Not all science can be cute. Some of it is just cool. This week, we've brought up planets in other solar systems a whole bunch of times. And today, we're just going to continue that theme. One of the things that is frustrating is we can only study planetary atmospheres when something is lighting them up. Sunlight through a planetary atmosphere works really well, but that means waiting for a planet to be aligned just right with its star. And it requires the star to not overwhelm the light coming through the planet's atmosphere. Ideally, we want a planet with an orbit aligned to carry it in front of its star from our perspective. And we want the star to be fairly faint. And we want everything to be moving fast enough that we don't have to wait too long from one planet passing to the next. And we also want all of this, to happen in a system that isn't too far away. That's a lot to ask of any one system. But it turns out that one little star with a mighty large planet is out there happy to comply. Discovered by the TESS mission, the planet TOI 1231b is a Neptune-sized world orbiting a small red dwarf every 25 days. And that system is just 90 light years away. Because this is a new discovery, we haven't actually made those atmospheric measurements yet, according to study collaborator Diana Dragmeyer. The low density of TOI 1231b indicates that it is surrounded by a substantial atmosphere rather than by a rocky planet. But the composition and extent of this atmosphere are unknown. TOI 1231b could have a large hydrogen or hydrogen-helium atmosphere or a denser water vapor atmosphere. Each of these would point to a different origin, allowing astronomers to understand whether and how planets form differently around M dwarfs when compared to the planets around our Sun. Our upcoming HST observations, she continues, will begin to answer these questions, and JWST promises an even more thorough look into the planet's atmosphere. This work is published in the Astronomical Journal with first author Jennifer Burt. The universe is vast, and it's always neat when it puts exactly what we need nearby. After a quick break, I'll be back to talk about two stars that were unexpectedly determined to be siblings. Scientists don't go looking for coincidences. And in general, when we find them, we don't trust them to be more than accident and chance. But sometimes, just sometimes, the things we find are actually related. Enter astronomers Jason Curtis and Marcel Aguero. Working in a larger multi-institutional team, these scientists were doing follow-up work on the planet-having systems Kepler-52 and Kepler-968. Both these systems have 3 planets orbiting a K-dwarf star, a star cooler and smaller than our Sun that is capable of living for billions and billions of years without really showing its age. This last characteristic is actually a bit problematic. When we look at systems with K-dwarf stars, we can't easily measure their age, by which I mean we can't measure their age. Instead, we guess, based on where they are and what they seem to be related to. And sometimes we guess wrong. Going into this study, it was thought that K52 and K968 were several billion years old and utterly unrelated, simply strangers passing in the night through the original Kepler observing field, which is actually somewhat near the Summer Triangle. You can go out and look at it right now. This star field, it's located in the region of the sky being studied by the Gaia Space Telescope, a telescope that can very precisely measure stellar distances, brightnesses, and motions. We know that stars form in clusters, as massive molecular clouds of gas and dust collapse and fragment. Over time, these clusters fall apart as stars at slightly different distances from the galactic center orbit at different rates. After enough orbits, the cluster stars, they may have formed together, but they don't stay together, and they become thoroughly mixed in with all the other stars of the galaxy. But while older clusters may not be obvious to the eye, not so old but oldish clusters can still be found using Gaia data, because all the stars will be moving together through the galaxy like a load of people released from a shuttle bus to zip toward an airport entryway. Some will race ahead, others will lag behind, but the members can be spotted by their similar motions. And if it's a sports team or tour group, they may also all be wearing identical clothes that help them stand out. While stars don't generally wear sports jerseys, all the stars that form together will share the same chemical composition. And that is something we can see with spectrographs. It turns out these two stars are moving together, share the same spectra, the same chemistry, and are part of a newly discovered star cluster that was named Theia 520. Other stars in this cluster, ones that it is easy to measure the age of, well, they revealed that these stars are actually just 350 million years old. These are young planetary systems where the worlds are still settling into their orbits, and now we have two systems that are nearly identical that we get to study. Essentially, we get to do a twin study just with stars. So the next time someone says, that's just a coincidence, remind them that sometimes there is something that is a cause behind those two things looking the same. Welcome back, everyone. I am so excited to be joined by two people who have, up until today, just been happy little Twitter avatars whose words and ideas I've gotten to follow. And now I find myself saying their names for the first time. Joining me are Sophia Gad-Nasr and Cathrin Machin. Welcome.
Hi.
Hey guys, welcome to be here.
Now, you are joining us because there is currently an amazing collaboration going on. Because, well, Cathrin, you're an artist, and Sophia, you're a scientist, and sometimes these things need to be mixed. Can you both please tell everyone a little bit about yourselves? I'm going to start with you, Sophia.
Sure. So hi everyone. I am Sophia Gad-Nasr, also Astropartigirl on Twitter, and I'm a cosmologist or astrophysicist, astroparticle physicist. I do all that stuff. Essentially, I study dark matter, which is a part of the universe that we can't see and makes up 5 times more stuff than regular matter does. And I try to figure out its properties. And currently, I'm trying to use it to explain these giant supermassive black holes that sit in every large galaxy. And we just don't get how they formed that big.
And that is amazing. We're going to talk more about that. But Cathrin, can you tell us a little bit about yourself?
Of course. My name is Cathrin Machin. Hi guys, it's really nice to be here, and thank you, Pamela, for having us on. I'm a deep space artist, but actually my background is in mechanical engineering and video game development. That's what I've been doing for most of my life. And yeah, look, I am dedicated to just getting space into people's homes and hearts. And I've got a particular soft spot for anything that's deep space related, so galaxies and nebulae. But also, obviously working on visualizing scientific data, because of course the thing is that a lot of that stuff out there you can't see with your own eyes, so you have to find a way to visualize it for people, because often they've got very complex situations as well, so it's nice to be able to visualize it for people.
And one of the things I really love is you are giving shape and form to something that we can't see. And Sophia, you have the task as a scientist of trying to be at least one of the blind humans trying to trace out the shape of an elephant. What are the ways that we use to try and explore dark matter?
Yeah, so let's talk. I guess maybe we could talk about how some of the ways that we know that it exists. I'm not going to get too much into detail, but like the most, I guess, well-known way is how stars tend to move too fast in galaxies. We have a really good sort of pretty large-scale size laboratory, if you will, for gravity, and that's our solar system. And so we expect gravity to behave a certain way, and we've tested it with experiments and stuff. And so when we look at stars in galaxies, they're just moving way too fast. these galaxies should fly apart. And so there must be something that holds them together and is adding extra mass to it. Other things that tell us that dark matter exists are these really cool things called gravitational lenses that prove Einstein's theory of general relativity, which is just, to put it, I guess, in kind of, I think, beautiful terms, it's just a way that, that something that says that mass bends space-time. And so it's kind of like the way that space-time reacts to having a massive object, kind of like the way that like your bed or a piece of foam or whatever would react if you were to place like a bowling ball on top of it. And so gravitational lenses are, you've probably seen images like Hubble deep space images, for example, or like these giant galaxy clusters, and then you see these warped sort of galaxies around them. These are actually galaxies that are way behind that mass. And so if mass didn't bend space-time, we shouldn't actually see that at all. It should be blocked in the same way that like if you were to place a cup behind a bush, you wouldn't be able to see it. But mass does bend space-time, and so we get these. So light is traveling sort of in straight lines, but it travels along sort of a curved space-time, and so you get these arcs. These are things that you can explain with modifying gravity, but there are some things that you cannot explain with modifying gravity, and you require dark matter for that. One of the pieces of evidence that we have is large-scale structure. So the way that structure has formed, and you can see it in the little snap there with the cosmic web, requires dark matter in the early universe. Otherwise, there would not have been enough time to form this, because in the early universe, everything's like a plasma, so light bounces off of everything except for dark matter, because dark matter doesn't interact with light, which is why we can't see it. And so in these little density fluctuations in space-time, all matter interacts with gravity, and so it all wants to kind of fall into these little pockets and coalesce, but photons come in and push regular matter out because they interact. And so dark matter happily goes in and coalesces and doesn't even see the light. Pun intended. It doesn't see it, and so it's able to do that and provide the seeds for what will form large scale structure that we see today. Another thing is the cosmic microwave background, and these are things that we like you literally require dark matter for. That's not to say that we have a full understanding of gravity. We might find something different. Like we know that we don't really have the full picture of physics, but you still require dark matter regardless what you do in order to explain these things. And so because we can sort of only trace it in these ways in the universe, what we do is simulations. And so we kind of essentially just put the physics in and throw a bunch of particles together, and depending on what kind of simulation we want to run, we allow things to sort of go under these physics and sort of speed up time, since we're kind of a snapshot in time, and we can't really like watch a galaxy evolve. We can only watch it as it is at the distance that it is away from us. So like we also see things in the past, which is really cool. The further back you look, the farther back you're looking in time. But we can't take something and evolve it, and so we go to simulations for that. And that's one of the biggest ways, I would say, that we can see dark matter.
Oh, you're muted.
Thank you. That is absolutely amazing. But unfortunately, we have to go to break. When we come back, I'm going to find out just how this collaboration that makes the invisible visible ended up taking root, and how people can take advantage of this to get themselves some pretty amazing artwork. Stay tuned, everyone. Welcome back, everyone. We are discussing how you make the invisible visible using art. Cathrin, you have a near impossible task to try and combine the physics of dark matter with your knowledge of what draws people into artwork and a desire to keep things as accurate as possible, all trying to wage war against each other in your head. What made you want to take on this kind of a challenge?
Well, this one specifically, I just, it's about funding research and making that possible. Is that what you'd like me to cover? Or?
Yes.
Yeah. Okay, great. And I think that academics have a big challenge is that they want to do all this really amazing work. But of course, while you're doing research, you also have to pay bills and rent and live and all of that other stuff that goes along with it. And I wanted to make sure that, Sophia going through challenges in grant funding and so on like that, was able to fully, put herself into the research that she was doing. And I approached Sophia about this opportunity. So one of the things we've been working on actually quite a while back was doing a little bit of visualization for no other reason than it was just going to be a little bit of fun. But obviously we've had very busy years, and I'm sure everybody has had an equally interrupted, disturbed year, given all the situation that's going on right now. Yeah. So it was something that sort of languished and was put to the side a little bit. And Sophia, is it okay if I go into the tweet and how it came about?
Yes, sure.
Okay, awesome.
It's out there in public.
Okay. Sophia's had a bit of a challenging year. I mean, more so than most people, and it through no fault of her own, has impacted some of her research earlier on, as far as how much she could get done. And she unfortunately, just as she was getting back on her feet, discovered that her funding for the grant that would cover the majority of her expenditure for the summer was cut for whatever reason. Nothing related to Sophia, incidentally, just a situation that unfortunately evolved. And it just put her in a very difficult position. And I think a lot of academics have this scenario where they need to go full out on their research and suddenly they can't because, for anyone watching that doesn't know, research is a full-time job already. And if you need to catch up on research, it's a time and a half. We're looking at 2 full-time jobs. Yeah. And then you have to work full-time to pay your bills. So it's very, very difficult to get all of that done in one time, as well as have the mental game on, as well as like doing something at the edge in the forefront of science. And obviously this news is devastating. And, 2.5 weeks ago, I saw the tweet and I looked at it for a long time and I was like, I can't go past this. I know that it was something we could do. Now, doing this kind of stuff, which is visualizing space and making it available to the public, because for me, it's all well and good me having it on an abstract website or just putting it out there. I actually want it in people's homes because here's the thing that modern day, we've got 2 situations. Firstly, consumer ability, just access to scientific equipment is significantly cheaper, actually. Yes. As the years go on, we've got these amazing telescopes. We've got these abilities to do, new satellites, new things going on, lots and lots of ability to gain data. But simultaneously, we're losing the ability to see the night sky through light pollution. So it's like on one hand we get access and on the other hand it's being taken away and at a very dramatic rate. Incidentally, 99% of people in Europe and the US cannot or are living in severe light pollution.
Yes.
So I really want to get it into people's homes because I feel like the universe and the stars should be available to everybody. You shouldn't have to, and in most people right now, if you did want to go and see, what's out there, it's a 5 or 6 hour journey. So, that's really why I'm doing this, because I want to get it into people's homes. So I've built a business, it's not just me on my own, incidentally, guys. I have a team of 6 people. We have created a process that I can make my artwork and get it out to people. And obviously, it's very difficult to do all of the back end logistics and customer support and all of that stuff while still doing, promoting science and actually getting time to paint, which is always a challenge because some of these artworks take. So that Crab Nebula actually was 6 months of painting. And so a lot of them, and that one in particular is accurate in the sense of all the different things are placed. I want it to look like the real thing, of course, but maybe just a bit zhuzhed up because it's art. So, I saw the tweets from Sophia and I just thought, what an amazing opportunity to change a situation from something that's a challenge into something that's a beautiful, beautiful way to this is the thing that I love. Firstly, everyone gets these most beautiful art prints that they can have in their home. And I rant about this all the time, but you can't get it's very hard to get really good space art. Like, don't get me wrong, of course, there's some amazing artists out there, but you can't go to your department store. You can't go to a general gallery. You have to find a specific person online in order to get it. If you go into Target or Kmart, you can get paintings and stuff to hang on your wall, but none of them will be space. None of them will show the dark matter web. None of them will show black holes. They won't show things that, in my opinion, are the most beautiful things in the universe you can't get hold of. And it makes no sense to me. So, and I really wanted to make it so that it was available to everybody. So in this process, everybody wins, of course. People get these beautiful art prints and they are printed on probably one of the most beautiful papers I've ever had the chance to use. And I know that's a weird thing to say, but when you feel it, it's really nice. And, research wins because the, portion of the funding goes to support, and it's such a great way to fund research. And the third beautiful thing is that you get to visualize things that are very hard to visualize. And you know what? It's interesting working with Sophia because, I've had I have to ask a lot of questions on like how things would roll out. And the questions that you probably don't get asked necessarily as a scientist because you're looking at different aspects of data. But it's like, how would so we were talking in particular about, dark matter halos collapsing into black holes and like how would even the dark matter be distributed, how would they fall in, if they were interacting. So this one above, it's two black holes. So it's a black hole that is at the center of the dark matter halo attracting another one in, and you can see the one on the far side is a little bit lensed, so it's warped around. So we were trying to figure out, should they be perfectly round? But no, it's got to have, gravitational lensing. So, and, very like different aspects of things that you wouldn't normally think about. And it was good just to go back and forth. And our chat log is extensive. Like it goes on for a long time. It's like a CVS receipt. And, it's just all these different things back and forth. And Sophia's drawing diagrams and I'm like, trying to and I'm a very visual person. I'm a pictures person. So, trying to you combine some of the words into a visualization. Anyway, I am so pleased with how everything came out. I know that it's not perfectly scientifically accurate, but for me, it captures I was trying to capture not just my excitement, but Sophia's excitement about how beautiful these things are. Because, when you look at the data, you see this infinite, amazing beauty. And it's hard to even convey that. Scientists spend all their time trying to convey it. And it's just nice to be able to put an image in front of people and people get, people are like, I get it. It makes sense. It's gorgeous.
and so the art that the two of you have collaborated to create is currently for a very limited time available through your Shopify site. You
That's
are
right.
shipping worldwide.
Yes.
And you have poster prints, you have masks. Was there anything else?
We have digital bundles because we really wanted to, of course, everyone that is on Zoom meetings now, you can have some cosmic Zoom backgrounds, or just on your phone. I mean, I'm just personally cover everything in space. I am thoroughly biased. But yeah, so those three things are available right now, and it closes obviously on the 13th, so very soon.
And this is something that's near and dear to my heart. I've written that same tweet of our grant went away. And it was the community that supports CosmoQuest, the audience to this show, and the Astronomy Cast, and several of our sibling programs that stepped forward and said, we will carry you. And we are able to make this television show because of the generous contributions of folks on Patreon and people who have supported us in many different ways throughout the year. This need to find creative solutions to funding. There's two parts to it. There's the scientist saying, I just want to understand our universe. And there's the person saying, I just want to help. I have an idea. And what I love is with the two of you, there was a pre-existing, you knew of each other, you'd communicated before. And it became a moment of, let me see how I can help carry you. And it's really a beautiful moment. Now, this is very temporary. What is your next big research push that you're going to be doing, Sophia? And we're running short on time.
Yeah, so actually one of the in terms of my research. Yeah, so one of the images is directly visualizing that, and the dark matter collapse into a black hole is essentially what I'm working on right now. I work on a type of dark matter that invokes sort of a dark force that has not been discovered. And so the consequence of having these interactions where it interacts via this dark force is that the central part of the halo can collapse into a black hole. And so we want to understand how we have supermassive black holes actually pretty early in the universe. So it's not so much the ones that we see today right now. It's that we find supermassive black holes 1 billion times the mass of the sun only 700 million years after the Big Bang. And that's just not enough time to form that from a regular, stellar mass black hole. And so we want to see if this can happen early enough in the universe, because from these dark matter halos, you can get an intermediate mass black hole. So one that's like 10,000, 100,000 times the mass of the sun. And so from that point, you would be able to accrete. So accretion is basically when a black hole eats. It just eats up matter. And so that's the most significant way that black holes grow. They also merge, and that's the merger that we kind of showed in there was really, I think, I would say for the purpose of beauty, because you get to see the accretion disks all swirly and the lensing going on. But if we're able to figure this out, then we'd be solving two problems. We'd be learning a lot about the particle physics of dark matter, which is something we still don't understand. And we'd be learning how supermassive black holes came to be. And so this is something that I'm extremely excited about, and really, really happy to have been able to put this out through Cathrin's amazing and brilliant creativity into this wonderful piece. And I'm just so grateful that I was able to do this with you, because this is how I'm going to be able to do this. So yeah,
this is amazing. And Cathrin, what are you doing next to enrich your art?
So I'm hoping to do a few more of these projects, actually working with scientists, maybe even more stuff with Sophia as well. But I'm actually building, in the beginning stages of building a chandelier based on the Gaia mission data of the Milky Way. The best part is that it's 8 meters or 13 feet in diameter, 3D printed in a crystal clear resin and suspended by thousands of fiber optics. So wow. Of course, we are in the process of funding as well, and it takes an extraordinary amount, because we've got to raise just over $250,000 in order to start the project really to its full extent. But we are making progress on the data side right now, which is very exciting.
That I want to someday see that, and I am not afraid to travel to your continent when we're past our current germ times. This sounds amazing, and I can't wait to follow everything the two of you are doing. Unfortunately, that's going to have to happen on another day. For now, this has been the Daily Space. You can find out more information on all our stories, including images and links, at dailyspace.org. Thank you all for being here. Bye-bye, everyone.